Hello and welcome back to Introduction to General Relativity. Today we're going to exploit all the hard work that we've invested in learning the mathematics of differential geometry to finally discuss general relativity. Before we get to the full formulation of Einstein's theory of general relativity, we'll have to make a couple of comments on special relativity and the consequences of the principles of the equivalence principle and Mach's principle that we are adopting in formulating general relativity. The first comment to make is that the equivalence principle itself implies that it's impossible in general to set up a family of inertial observers to measure the gravitational force. We can't, and the problem is we just can't insulate an observer from gravity. Any observer, according to the equivalence principle, will move in exactly the same way as a test body, and there is no natural background motion to compare with a test body. So that's the main problem with thinking of gravity as a force within general relativity. So this is actually a fundamental hypothesis in general relativity, and what I'll do is I'll write this out a little bit more explicitly and name the fundamental hypothesis of general relativity explicitly. So let's sort of review general relativity as we've somewhat vaguely formulated it, built on the equivalence principle and Mach's principle, and now make it much more precise. Indeed, this is the formulation that we're going to be carrying forward in our discussion of Einstein's general theory of relativity. So the fundamental hypothesis of general relativity reads that space-time is a manifold M on which is defined a Lorentz metric G. We'll say GAB to emphasize the fact that it's got two tensorial components. And further, before I say the further, I should point out, as a side remark, that the manifold M can be a lot more general than just Minkowski space. So incorporated into the fundamental hypothesis of general relativity is the fact that spacetime itself need no longer be flat. In fact, it can be topologically different from Minkowski space. So that's the first part of the fundamental hypothesis of general relativity, but there's more to it. There's also the fact that space-time is not necessarily flat. You could have topologically different manifolds, but they could be still flat. But here it's allowed in the fundamental hypothesis of general relativity for space-time to be not flat, so not necessarily flat. And also the world lines, and this is where we incorporate the equivalence principle, of freely falling bodies are geodesics. Of the curved metric G. So this is going to be the fundamental hypothesis of general relativity for us going forward. And we're going to build general relativity on this fundamental hypothesis. We'll see that we're not yet quite there yet. We need a way to build equations of motion for various physical systems. We'll need principles to guide us in selecting these equations of motion. Well, further, we also need to provide a quantitative way to describe the equation of motion of spacetime itself. And so that will require the addition of Mach's principle. Anyway, for the next part of this lecture, we're going to start building on this fundamental hypothesis. Now, it's worth saying that in certain situations, it is sort of possible to measure the gravitational force. And that's something that we should comment on explicitly. So for cases of time translation symmetry, so if for some reason you have a setup where your system is invariant under time translations, or your background, you have somehow a strong background that's invariant under time translations, one can define a preferred setup. Background family of observers, of inertial observers, and you can therefore, or thereby, sort of measure a gravitational force, but with only respect to this family. So it's possible, and what situation are we talking about? Well, we're talking about here on Earth. So we have one heavenly body, the Earth, where this heavenly body is in absence of the rest of the universe. It generates a gravitational field that is invariant under time translations. And then we can set up a preferred set of background observers with respect to which we can measure the gravitational force of the Earth, and then we're all happy. And so that does apply in this very particular situation of one heavenly body. However, the minute we have two or even three in motion, then the system is no longer invariant under time translations, and it's impossible to set up a preferred background set of observers to measure a gravitational force with respect to. So although the fundamental hypothesis of general relativity pretty much excludes setting up a preferred background observers, there are, we can still measure things to do with gravity. So I better write that down. While we cannot measure the gravitational force directly, so while we can't measure the gravitational force in general situations, we can always measure the relative acceleration of nearby geodesics. That's well defined. And hence we can speak of tidal forces. Meaningfully in general relativity. So that's an important observation. In fact, it's a critical observation when it comes to formulating Einstein's field equations. So given this fundamental hypothesis of general relativity, how do we actually determine the laws of physics in general relativity? Well, there's two key principles that you can employ to determine the laws of physics. I mean, we don't have to do everything in a vacuum. We can really take guidance from two key principles. I mean, these are not these two principles are not like 100% mathematically rigorously well defined, but they are so helpful as guiding principles that you pretty much can uniquely identify the correct laws of physics for the situation you're interested in. So what's the key principles? So the first one is the principle of general covariance. That's the first core principle that that one can and should use to determine equations of motion or laws of physics in general relativity. And the principle of general covariance says that only the metric basically is allowed to appear as a representing the space-time geometry in equations of motion. So only the metric and quantities derivable from the metric may appear or are the only space-time quantities that can appear in laws of physics. Laws meaning equations, right? So if you want to formulate a law of physics and you want to make reference to the geometry, space-time geometry somehow, like, I don't know, in terms of position or something, then you better not be referring to anything other than a quantity derivable from the metric. So in particular, you're not allowed to refer to, say, the position in some coordinate system. That's already been captured earlier qualitatively in the principle in our discussion of the core principles underlying special relativity, for example. Now that's not quite enough to help us in formulating the laws of physics in general relativity, but here's the second principle that more or less does it for us, and that says that the equations of physics, if you kind of come up with some equations of physics in GR, they must reduce to their special relativity versions for the case where GAB is flat, right? Yeah, that seems like a pretty safe principle. Because if that weren't true, then we wouldn't accept special relativity as somehow a limiting case of general relativity. So we have to point out that these two principles are somewhat imprecise, and they don't actually uniquely define the laws of physics or determine the laws of physics, but they are very, very helpful as guiding principles for identifying candidate laws or natural physical laws. All right, so according to these principles, let's get started in identifying the laws of physics for the motion of free particles. So we've got we're going to continue to represent physical quantities by tensorial objects, just as we do in special relativity. So the velocity is a vector, stress energy is a tensor, that kind of thing. Yeah? So here's a couple of bullet points that will summarizing this statement. So for example, particle motion is represented by time-like curves. What's another principle? The forward velocity of a particle will continue to be represented as a tangent vector to a world line. And unit means we're measuring it with respect to the metric. So these kind of quantities we don't posit new quantities to define old concepts, but we do have to update the equations of motion, or amend the equations of motion. So, we're no longer doing Newton's laws here. So we have to update the equations of motion. And how do we update the equations of motion? Well, for free particle, I'll just, before I jump into that. So while we don't change the tensorial quantities representing physical properties in special relativity, we do update the equations of motion. And in particular, free particle motion, or the free particle equation of motion, becomes the geodesic equation. That's the first updated law of physics. So in the absence of any exterior forces, external forces, a free particle will move along a geodesic as per the fundamental hypothesis of general relativity. And we even have an equation of motion determining a geodesic now, and that is determined with respect to the derivative operator delta determined by the metric g. And so we can now define the acceleration analogously. So the acceleration is given by, well, the change along the world line of the velocity. So if it's, which is 0, right, for something in a free particle. And when it's not 0, then we say that a force is acting on the test particle. F, what's the force that acts on the particle? Well, it's the force is just m, the inertial mass of the particle, the rest mass of the particle, multiplied by the acceleration. So it's not Newton's second law, but looks pretty close. We've just updated the notion of acceleration to be defined in terms of the derivative operator associated to a metric. Accordingly, we also define the form momentum of the particle how do we define that? Well, you just take the rest mass and multiply it by the unit vector representing the tangent to the geodesic that the particle is following. If it's freely moving. And now we've got the form momentum, we can define the energy. But now you have to be a little bit careful. The energy, as it'll turn out, cannot be defined globally. This is a really important property of general relativity, but we can certainly define the energy locally. So the energy, now who determines the energy? Well, an observer determines the energy. So the observer who can determine the energy of the particle has to be present at the particle's world line, right? We'll see, I'll explain why in a second. So the observer who's going to try and define the energy has to be present at an event on the particle's world line, and that observer will determine the energy to be minus the momentum of the particle, the scalar product of the momentum with the velocity of the observer. So of course an observer who moves with the test particle will say that the particle has no energy, well, apart from the rest mass energy. So now, why can't we define energy for a particle somewhere else, not present on the world line, or on the observer's world line? Well, because space-time is curved, the parallel transport is path dependent. So there's no notion of a natural family of inertial observers, and a given observer cannot, in general, define the energy of a distant particle. Because you see, you need two vectorial quantities to define the energy. You need to multiply the momentum of the particle and the velocity of the observer, or take the scalar product. And because in a general curve manifold, parallel transport is just not, it is just path dependent. So you might try and formulate a protocol whereby you measure the energy of distant particles by only moving along certain world lines, but in a general curve manifold there is no distinguished preferred background frame of inertial observers, so there is no real way to distinguish a preferred parallel transport path to measure the energies of distant particles. So in this summary of the kinematics of single particles, we've already witnessed the application of the two principles determining the laws of physics in general relativity. The metric does appear in these expressions, certainly implicitly in the definition of the derivative operator, and also in scalar products between the momentum and the observer for velocities and momenta. And also it's pretty clear, I hope, right, that these equations of motion reduced to their special relativity versions. Just replace the derivative operator determined by the metric by the one determined by the flat metric. And so you can see that in applying these principles, we are somehow exploiting a following set of what we might call minimal substitution rules. And we can, make this a bit more explicit by saying that general relativity friendly equations of motion, how might you find them? Well, there's a kind of let's say usually, not always, right? They can usually be found by applying the following minimal substitution rules. So in special relativity, the flat metric eta AB gets mapped in general relativity to just a general metric GAB. And in special relativity, when you have a derivative operator, just your usual derivative operator, in general relativity you replace that with the covariant derivative determined by the metric. And in this way, we can build up a whole bunch of hypothesis equations of motion for field theories and beyond. So let's give some examples of applying these minimal substitution rules. Well, one of them is, this is going to be simpler than the field theory that will occupy us for the rest of this course, because the field theory of principal interest in general relativity is that of fluid dynamics, which is a pretty complicated field theory. There's several fields involved in formulating fluid mechanics. Before we even do fluid mechanics, let's experiment with a far simpler field theory, namely a scalar field theory, known as the Klein-Gordon field. Let's apply these minimal substitution rules to see what we get, see what kinds of equations of motion we get. So in special relativity, the Klein-Gordon field is determined by a Lagrange density. You don't need to worry about Lagrange densities if you don't know about Lagrange densities yet, because I'll write out the equation of motion anyway. So by varying this Lagrange density, you get the equation of motion. That's the thing that we're going to modify right now. You get the equation of motion delta A phi minus m squared phi is 0. So that's the Klein-Gordon field in special relativity. Plays a hugely important role in quantum field theory as well as in classical field theory. Now, how might you get the general relativity version? Well, in general relativity, remember what we have to do? We have to replace the delta A's with the big covariant derivatives. So just looking at that equation of motion, the first thing you might guess, and you're welcome to guess it, is just to replace deltas with covariant derivatives, and there you go. That's one perfectly well-behaved general relativity friendly formulation of scalar field theory. The stress energy tensor for this particular scalar field theory, a couple of ways you can argue what the stress energy tensor is. One of them, if you know anything about classical field theory, is to apply Noether's theorem with respect to the symmetries of translation. Or you can just believe me, that's also fine. Another clever way to get the stress energy tensor is to vary the metric of the action. It'll get you the stress energy tensor as well. There are some differences between these ways of getting the stress energy tensor, but for here we end up with the following conservation equation. I'll say conservation, but I'm going to argue later it's not actually a conservation equation. You end up with the following equation of motion for the stress energy tensor of the Klein-Gordon field, namely that the divergence with respect to a derivative operator determined by the manifold is 0. Now, it's important to note that this is not the only generalization possible. There are, in fact, other generalizations that you could very meaningfully add to the equation of motion. For example, you could add the term to the equation of motion, which is just some constant alpha times r, the Ricci scalar, times phi. That term certainly reduces to its special relativity version in the case where the metric is flat, r vanishes, and it contains only the metric in a nicely contracted way. So that's a possible term you could add. It's not the minimal substitution, but it is a possible substitution. So there are, and sometimes these added terms, it is possible to argue that they are in fact more appropriate to describe certain physical situations. Okay, so that's a kind of warm-up. The Klein-Gordon field is a kind of warm-up problem for the field theory that is of primary importance in general relativity, in particular in cosmology, namely that of a perfect fluid. So the perfect fluid is a field theory. It's a field theory with a velocity field, a pressure field, and a density field. So there's lots of fields interacting. It pertains to a continuous distribution of matter. And the way we describe the state of this matter is with the stress energy tensor. So if you remember the discussion of the stress energy tensor several lectures ago, it describes the density of positions and momenta of all the particles that make up the matter. And the stress energy tensor of a perfect fluid has a certain form, and it's this form here. And you can argue that this is the correct form by taking the continuum limit of the stress energy tensor of a bunch of particles. So here rho is the density, so it's a field now. P is the pressure, and UA is a velocity field. And it represents the fall velocity of the fluid. Now, the equation of motion of a perfect fluid you can find it by taking the divergence, the four divergence of the stress energy tensor. So that's the special relativity way to describe a perfect fluid. You describe it by the stress energy tensor, and the equation of motion is just the four divergence is vanishing. And as I'll argue later, or as I'll remind you later, that just pertains to the conservation of energy. However, in general relativity, I de-emphasized, this prior discussion of the stress energy tensor, I de-emphasized the role of for divergence being a conservation law, because as we'll see in general relativity, we have to revise our understanding of these things a little. So in general relativity, how do we get the stress energy tensor of a perfect fluid? Well, it's the same story. We apply the two principles above and the minimal substitution rule. So there was a metric, now we've got to replace our metric with GAB, and nowhere else do we have to do anything. And we impose guess, right? You know, you have to make it clear that the minimal substitution rule is a guess, and you have to provide independent arguments why it's correct. So the simplest equation of motion you can impose on the stress energy tensor in general relativity is that the covariant derivative contracted on the first argument is 0, on the first tensor argument leg is 0. I might call this star star. Now, these equations of motion that I've written here, there's 16 of them in the red box there, 16 equations of motion for the stress energy tensor. But we can actually, since the stress energy tensor is symmetric, we can reduce the number of equations of motion and put them in a slightly more familiar form. And you can do that by projecting the equation onto components parallel and perpendicular to u. And when you do that, you get the following two equations of motion, which might look slightly more familiar. One is like the conservation equation, and the other one is like Euler's equation, pertaining to the derivative of the velocity field. You check in the non-relativistic limit that this all, first you go to the special relativity limit where you replace g with eta and delta, the covariant derivative with delta, and then you can go to the non-relativistic limit where the speed of light is much greater than any velocity in your setup, and then you'll end up back with the conservation law, Euler's equation, that you would know from non-relativistic physics. So now I'll just comment on the interpretation of the stress energy tensor in GR. So it's important to note that there's a distinction in how we are allowed to interpret the stress energy tensor in general relativity as opposed to, or as compared with, special relativity. So the first thing to note or to do is to just revise or remind you how we interpret the stress energy tensor in special relativity. So in special relativity, an observer with full velocity VA interprets the quantity TAB, VA, VB as an energy density. More specifically, the mass energy density per unit volume for the observer. Okay, you can go ahead and just verify that as an exercise, right? We talked about, I introduced the stress energy tensor several lectures ago, and you can take that definition that we supplied there and just check that interpretation. Further, right, if XA is orthogonal to VA, then the quantity minus TAB VAXB is the momentum density of matter in the XA direction, or is interpreted. So dA, the forward divergence of the stress energy tensor in special relativity, then gets interpreted, or may be interpreted, as a conservation law. So how do you do that? Well, you apply Gauss law. And then you'll be able to interpret Gauss's law as imposing a conservation law for a current. Now, before we do that, we have to say a couple of words about how to set up this situation. Because we are in special relativity, we can set up, or we assume that we can, in principle, set up a family of inertial observers which have a certain property, namely that they all have parallel fall velocities. And what does parallel mean in this context? It just means if you take the derivative of the fall velocity field defined by this family of inertial observers, that fall velocity, that derivative is zero. So here's a picture of this. You've got fall velocity observers. You've got observers all marching forward in a nice grid of observers, and they're all moving parallel to each other with respect to some inertial reference frame. When you have this velocity field determined by this family of inertial observers, then you can set up a current. We can set up the following current. JA is just minus TAB contracted with V. Right? So we've got a current where V is the velocity of these, velocity field is these observers, so we have a current density. And now this the equation dA TAB is 0 implies the divergence-free equation dAJA is 0. So JA is really like a current. And then you can integrate that equation to derive conservation laws. So you set up a fictitious pillbox in space-time, and then you can integrate this current and apply Gauss's law to learn conservation laws for the forecurrent. Now, this is the story one tells in special relativity to interpret the law of motion, delta A TAB, for a stress energy tensor. However, in general relativity, we have some challenges, some problems that prevent us from interpreting these things in the same way. We can still represent families of observers, with a velocity field. So a family of observers may still be represented by a velocity field v, where v is unit and time-like. Then the condition that the fall velocities, however, are parallel, that they're all moving, parallel to each other, has to be changed. According to the minimal substitution rule, we would guess that the condition for a family of observers to be moving parallel to each other is the covariant derivative of the components of the velocity field is 0. Or, equivalently, that d delta A VB symmetrized is 0. So this is an equation we're going to meet a little bit later in the course, called Killing's equation. And so this looks all fine, right? Maybe we can always solve Killing's equation, right? And then maybe we can set up this current vector J, and then we can infer the conservation of this forecurrent, the global conservation of this forecurrent from a kind of Gauss law. However, and this is I already discussed this at the beginning of this lecture. In a curved space-time, it is generally impossible to find such VAs. So it's generally impossible. I mean, it is possible for Minkowski, but in general, it is not possible to find a family of observers such that they are unit time-like and that this Killing's equation is satisfied. And a really crucial counterexample that really is pertinent to the space-time that we live in is d-Sitter space-time. In d-Sitter space-time, it's impossible to find a global time-like Killing vector field, which would be the thing solving this Killing's equation. That means you can't define a notion of global energy, and therefore you can't infer from the equation of motion delta A TAB equals 0, you can't infer strict energy conservation. Physically, you can interpret this also physically as saying that tidal forces do work. And how do tidal forces act on something? Well, via the gravitational field. So global energy conservation is not implied by the equation of motion of a perfect fluid in general relativity. However, it is possible to still regard this equation of motion as a local conservation of energy. So if we name it star star, which I have, so you are allowed to regard the equation star star, which is the divergence-free, general relativity divergence-free equation of motion for the stress energy tensor. You are allowed to regard it as a conservation law locally if the gravitational field is sufficiently small and the region which you're looking at is sufficiently flat, so that you can set up effectively a local family of inertial observers, background family of inertial observers, which are moving parallel to each other. Okay, so that's a little tour through a couple of three equations of motion in general relativity, and how to discover them via these principles of general covariance and the principle that equations of motion ought to reduce to the special relativity versions when the gravitational field is sufficiently small. Now these principles only get you so far. They get you far enough that you can work out equations of motions for various physical situations, but there's one physical quantity which it doesn't tell you how to quantize. Not quantize, sorry. There's one physical quantity which it doesn't tell you how doesn't tell you the equation of motion of, and that is namely space-time itself. So that brings us to the topic of Einstein's equation. So, as I've emphasized throughout this course, space-time in general relativity, space-time itself is dynamical, which means it changes in response to things. So we need to have an equation of motion for space-time. And therefore we need an equation of motion for something quantifying space-time, and according to the principle of general covariance at least, this had better be an equation of motion for the metric. And that's a core equation of motion that we need in order to move forward in formulating general relativity. And how do we find this equation of motion? Well, we need some kind of principle to guide us, and that's where Mach's principle comes in to play. That space-time geometry, one reading of Mach's principle would be, is that space-time geometry is influenced by matter distribution. Okay, that's a key principle. Great. That's sort of helpful, but not, right? I mean, thanks, but no thanks. We need a bit more to make this quantitative, right? At the moment, it's very qualitative as a statement. We need an actual equation of motion that's involving the metric and some derivatives maybe, or something like that. And the trick, the clue, is to look at tidal forces and how they're calculated. And in fact, we're going to look all the way back to Newtonian physics for guidance. So you know, we somehow have in the back of our minds in this discussion here that we have a heavenly body and we have two test particles moving in the gravitational field of this heavenly body. Here's one and here's another one, and they're on slightly different orbits. That's an appallingly bad rendition of two test particles on slightly different orbits. Anyway, you get the idea. Okay. So I'll really try to get this a bit better. So the Earth, let's say it's the Earth, and a test particle is a little spaceship. The Earth is at one of the foci of the ellipse, and then we have another orbit of another spaceship that's nearby. And so along this orbit, these two spaceships move relative to each other. And you can solve, go through the whole Keplerian thing and work out the orbits of these two particles, and you can set up the equation of motion for the relative separation vector. So if you do this Newtonian, what would Newton tell you to do? Well, Newton wouldn't tell you, but this is how you would do it in the Newtonian way. Firstly, in the modern Newtonian way, you'd describe the gravitational field by the potential, gravitational potential phi, and the tidal acceleration vector you'd call A, right? X is the relative separation, and the tidal acceleration, like how do these two particles accelerate with respect to each other as they orbit around the planet? Well, that's it's determined by the following equation here, which is a good exercise in your orbital mechanics. And this x is the separation relative. Okay, great. So that's how you calculate the tidal acceleration in Newtonian physics. Well, actually, in general relativity, we've also solved this problem with the geodesic deviation equation. Remember, these two freely falling bodies, these two spacecraft, they're each moving on a geodesic of this gravitational field. And we know that if they're infinitesimally close, how two geodesics accelerate and decelerate with respect to each other. It's directly related to curvature. And the curvature is quantified by the Riemann curvature tensor, and the relative acceleration is quantified by this geodesic deviation equation. So here, v is the fall velocity of the particles, and x the deviation. And so this suggests, doesn't prove, but it strongly suggests a correspondence. You know, the correspondence that it's suggesting is, well, it's just take this, strip off the relative separation vector from both sides, so to speak, and then you ought to have that the curvature is related to the derivatives of the gravitational potential. With the velocity thrown in there of the orbiting particles. But phi is determined by rho, the distribution of mass energy. In Newtonian theory. And the equation of determining the distribution, determining the gravitational scalar potential is this Poisson's equation. But remember, right, you know, I went to some lengths to explain the interpretation of the distribution of mass energy or energy density and that's described by the stress energy tensor. According to TAB, VA, VB, where V is the velocity of the observer, relative to the matter at that point along the observer's world line. So we've attained a correspondence between the stress energy tensor and the energy density of matter. Thus, we have a suggested correspondence between curvature and the stress energy tensor. And that's exactly the kind of thing we've been looking for. So we put it all together. We have the stress energy tensor on one side, we have the VC and the VD, the velocity vector of the inertial of the observer moving through this gravitational field. And that implies, right, the following equation, namely that the Ricci tensor is determined by the stress energy tensor. Now, I'll put a question mark and an exclamation mark there because it's not correct. You know, this argumentation, while very, very beautiful, has a flaw. Now, this was in fact Einstein's original equation. However, he very quickly realized the flaw. It has a flaw, pretty glaring flaw, namely that the divergence of this stress energy tensor is not equal to 0. And the reason is because of Bianchi's identity. Because of the Bianchi identity, we have that delta C RCD, Ricci tensor minus a half GCD times by the Ricci scalar is 0. So the only way to reconcile the equation of motion for the stress energy tensor and this equation I've put the square exclamation mark next to would be if the Ricci scalar vanishes. Okay, but that's not satisfied by most interesting manifolds. But the resolution is incredibly simple. Namely, consider instead the equation GAB, the Einstein tensor, which is RAB minus a half RGAB equals 8 pi TAB. So this equation is consistent with the divergence condition on the stress energy tensor, and it reduces in the right limits to the same consequences that I discussed above. And this indeed is the resolution to the goal or the puzzle above, and provides the connection between spacetime geometry and the distribution of matter. This equation now bears Einstein's name. It's called Einstein's equation, or Einstein's field equation. So in this lecture, I've taken you along the path of trying to understand how to generalize laws of physics that we know in the limit of special relativity, how to generalize them to the case of arbitrary manifolds and hence find their general relativistic counterparts. Also, by taking Mach's principle and making a quantitative version, we're able to discover, as Einstein did, that there is an equation relating space-time geometry as quantified by the metric and the distribution of energy density, stress energy density in space-time as quantified by the stress energy tensor. And this led extraordinarily elegantly to an equation known as Einstein's equation. This amazing equation will be the focus of the rest of this course. We're going to take aim at trying to solve this equation. We will fail completely, except in a couple of very, very special cases. And we'll also spend a long time interpreting this equation in various physical situations. It's really this extraordinary equation. It's very, very difficult to sort of overstate the amazing significance of this equation and the formulation of general relativity as I presented it today. And particularly amazing, and I hope you'll share this sense of wonder as we go through this course, particularly amazing is how everything holds together in a self-consistent way. We'll see that very clearly in the coming lecture. But for now, that's it. Thank you very much. See you later.